Hi students, so today we start lecture 34 in our aerospace engineering course, and today I'm going to talk about the rate of climb. Now in previous lectures we have discussed about the steady level flight type of situations, and of course you do not want to fly in steady level flight all the time. Sometimes the aircraft needs to climb also. So today we are going to look at that situation. I'm Dr. Ranjan Ganguly. Now here I have made a diagram about the forces which are acting on the aircraft when it is in climbing flight. So essentially we are going to presume steady unaccelerated climbing flight. So in this kind of situation, if we take an aircraft here, there is a typical horizontal line and then there is a flight path. Now the angle between the horizontal and the flight path is some angle theta, let's say, and you of course know that the thrust is going to act along the flight path and the drag is going to act in the opposite direction as far as the thrust is concerned. There's also going to be the lift which is going to be normal to the flight path. So of course we are assuming that the velocity is coming from the flight path direction. And finally there is going to be the weight of the aircraft which is going to act toward the center of the earth. So this is the direction of the weight, and the angle of the weight with respect to the vertical is also the same theta which you see here, and this is coming from geometry. So this is a typical diagram of an airplane in climb, and very often you will see airplanes climbing, specifically when they are taking off from the airport and so on. And if you have been to any air show, you will see that military aircraft such as the one I have shown here, they tend to climb very fast, so they are capable of high rates of climb. So let's define what is the rate of climb. So essentially we use the symbol r/c to show rate of climb. And again, looking at the same figure here, we know that the velocity v infinity is along the flight path, and then there is the horizontal here, and then there is this angle theta. So this is coming from geometry. And then what we do is that we define rate of climb as v infinity sine theta, which is the vertical component of velocity. So essentially that is the rate of climb. It's the vertical component of the velocity of the aircraft. So we are going to look at the possibilities of climbing pretty fast. So naturally if you are a pilot, you want to climb as fast as possible. In certain situations it can save you from trouble. For example, if you are approaching a steep mountain range, a very steep climb can get you out of that mountain range, and so there are many situations where a rate of climb is very important. Also, for example, if you are taking off from a runway, you want to climb pretty fast so that you can get off from all those tall buildings which are often there in the downtown where airports tend to be situated. So let's now look at the climbing flight equations, and we are going to derive expressions for the rate of climb from these equations. So again, looking at this picture I discussed before, we can now do an equilibrium of the different forces. So let's do an equilibrium in the flight path direction. So that's going to give us T, the thrust, is equal to drag plus W sine theta. So W sine theta is the component of the drag or component of the weight in the drag direction. So essentially we see that the thrust is balanced by the drag and the component of the weight in the drag direction. So that's the component given by T is D plus W sine theta. That's the equation we get in the flight path direction. Now if we look at the vertical direction, there I'm going to get the equation L equals W cos theta. So essentially that's the component of W in the lift direction. So these two equations give me the force balance situation here, and recall that compared to our previous discussion about steady level flight, now we have the angle theta in both these equations, and therefore the equations are slightly more complex. So do remember that when we had the level flight condition, theta was equal to 0, so thrust was equal to drag and lift was equal to weight. Those were the simple equations which we used for our calculation of some of the power required equations and so on for steady level flight. But now if we are in climbing flight, we see that thrust is greater than the drag and also the lift is lower than the weight from these equations. That's the general situation if theta is any given angle. So one of the things we can immediately see from this equation is that you are going to be able to climb only if the thrust is greater than the drag. So essentially thrust is going to play a very important role in developing a good rate of climb for the aircraft. So again, to explicitly put this thing in your mind, I have shown here a typical aircraft engine. So for example, if you have a jet type of engine, then that's going to produce a lot of thrust, and so this thrust is going to help you to get climbing flight. So many of the time you will see, especially if you go to air shows and all, the engines of many of the aircrafts are very powerful, and therefore they are capable of rate of climb which is at a pretty good value. So now let's go back to all the mathematics. The equations were very simple. The equations in this case were T equals D plus W sine theta and L equal W cos theta. So what I do now is I take the top equation, the equation with thrust, and I multiply it throughout by V infinity. So that's the equation here. So T into velocity is d into velocity plus w into velocity sine theta. So this is the equation multiplied throughout by velocity, and so I get this equation here, and then what I do is that I divide this equation by w. So let's do that here. So I can write the term tv infinity minus dv infinity divided by w equals v sine theta. So all I have done is I have rewritten this equation from the forced balance in this form. So why did I write it in this form? The aim of writing it in this form is that I have expressed it in the form of rate of climb. So do remember from our previous picture that rate of climb was v infinity sine theta, and therefore now I know that v infinity sine theta, or the rate of climb, equals Tv minus dV by W, and you immediately know that Tv minus dV is the excess power. So this is the excess of the thrust over the drag, and so there is sufficient power which you have in terms of the engine that you can actually generate excess power, and only if you have excess power, that means this is a positive quantity, are you able to sustain a rate of climb. So that's something very important to remember, is that rate of climb is excess power by weight, and therefore only if excess power is present are you going to be capable of rate of climb. So now from this equation I can immediately get one more fact, that maximum rate of climb is going to be maximum excess power divided by W. So all I did here is that I took the excess power and applied the max operator on both sides of this equation. So this is an equation which now we are going to see pictorially for the propeller engine aircraft and the jet engine aircraft. So let's first start with the propeller aircraft. So you remember from our previous lectures that the propeller aircraft has a typical available thrust given by this blue line here, that is PA, or this is the available power, and the required power given by this red line, that is the PR. And so wherever these two lines intersect, that's the Vmax, or the maximum velocity as far as the aircraft can fly. Now if we see the difference between these two power curves, then that is the excess power. So that is the available power you have that is in excess of the required power. So essentially your rate of climb can be obtained by this particular philosophy. So if at any velocity you want to find the rate of climb, you find the excess power and you divide it by weight. And so if you do this either graphically or numerically, you can find the location of maximum excess power from this graph, and then you can get the maximum rate of climb from that particular graph. Now let's turn to the jet. So in the case of the jet, you know that the available power is given by this blue line here, because this power is actually Ta into velocity, and because it's multiplied by velocity, it tends to go through this 0 point. Now the required power is the red line, which is given by this here. The maximum velocity is given by this green line, that is Vmax here. And so what you now have is the excess power is the difference between these two graphs or these two lines, or rather I would say the line and this graph here. So if I am at a particular velocity and I want to calculate the rate of climb, I can essentially find the excess power at that velocity and I can calculate the rate of climb there. And if I do this at several points, or I can pictorially see which is the maximum excess power location, then I can get the maximum rate of climb from this particular graph. Now do remember that all these graphs I'm showing here are essentially at a particular altitude. So these are at a particular height, and so if you are trying to do this at different heights, you would actually have to obtain various graphs according to that. So at each different height you will have different curves for PA and PR, and so the rate of climb, the maximum rate of climb are all going to be different. So now let's look at the difference between the jet and the propeller qualitatively. So here I am looking at these two plots. So these are both power versus velocity plots here. So if I look at the propeller situation, which is on the left hand side here, I can clearly see that excess power is quite significant, especially at the lower speed regime. So when you are at lower speed regimes, actually the propeller aircraft have a lot of excess power. In the case of jet, of course, the way this PA curve is there, it's kind of low at lower velocity points. So what happens is that you have more excess power at higher velocity points. So essentially, if you are in a jet and you want to climb at a high rate of climb, you need to be in a higher velocity region. But in the propeller, you need to be in a lower velocity region. That is why propellers are sometimes attractive if you are trying to fly in low velocity type of situations or climb in low velocity type of situations, including from airports, which essentially involve shorter runways and so on. Now there's one more way to look at rate of climb. We can try to plot the rate of climb with respect to the velocity, which I have done here. Now the curve goes something like this, which is given by the red line. Now of course you know that the rate of climb will become 0 at the point Vmax, because at Vmax the PA and PR curves are intersecting. So essentially the excess power at this point is 0, so rate of climb is 0. But then if you are flying below the Vmax, there is excess power, so the curve goes up like this. And then at a certain point you need, or you reach maximum rate of climb, and this corresponds to the Vmax rate of climb velocity. And this is of course for a particular given altitude. In all these cases, remember, these graphs are for a given value of h. So it could be at sea level, it could be at 5,000 feet, it could be at 10,000 feet. The curves would be different corresponding to those situations. So there's one more way to look at this concept, and that is to look at two different velocities. So again, let's go back to our starting diagram, and now let us look at the vertical velocity and the horizontal velocity. So in the case of the vertical velocity, which was also the rate of climb, I can write it as v subscript v. This is v infinity sine theta, and I can write the horizontal velocity as v infinity cos theta. So these two components are very important, and what I'm going to do is I'm going to plot these two components in the next graph. So this is a graph between VH and VV. So VH is on the x-axis and VV is on the y-axis. Now in the previous slide I defined VH as V infinity cos theta, the horizontal component of velocity, and VV as V infinity sine theta, which is also the rate of climb, and it's the vertical component of velocity. Now if I were to plot this graph, what I'm going to get is I'm going to get a locus of a lot of points. So let's look at different points here. Let's for example look at point B. So if you are at point B, what happens is that point B, the coordinate as far as x is concerned, that is simply VH or V infinity cos theta, and the coordinate in the y direction is VV or V infinity sine theta. So if I were to square these two from the law of triangles, I would get V infinity is essentially the hypotenuse or the distance from the origin to the point B. So this is the value of the V infinity or the speed of the particular aircraft. So this angle of course is also theta, which you can straight away see here from the definitions of Vv and Vh, and so we can get a very good estimate of this point B here. Now if you keep moving, you will reach a certain value here, and this value corresponds to the maximum rate of climb, because do remember that rate of climb is same as Vv, and Vv is a maximum here. So the point A corresponds to the maximum rate of climb, and then if you keep going down here, there's a certain point C here, and this corresponds to the value of theta, which is maximum. So this is the maximum angle of climb here. So to remember that the maximum angle of climb is not the same as the theta required for maximum rate of climb. These are two different values. You can see it from the graph. So this particular graph is known as the hodograph, and it is a nice way of looking at this whole concept pictorially. So let's summarize today's lecture, which was quite important. We saw that the rate of climb is the vertical component of velocity of an airplane. Excess power is needed to climb, and excess power essentially means that your engines have to be pretty powerful. Now we also saw that propeller planes have more excess power at low speeds compared to jet planes. So this makes propeller planes attractive at low speed regimes and jet planes more attractive at higher speed regimes, especially if you want to have good climbing flight performance. We also saw a particular new graph known as the hodograph, which is a plot for the horizontal velocity of the airplane versus the vertical velocity. And also we saw that there is a certain angle, theta max. It is the maximum angle of climb at which the airplane can maintain steady flight. So this can sometime come in handy if you are flying, you suddenly encounter a huge mountain in front of you, and you need to climb so that you can not make a collision with this mountain. So in that case, theta max is going to play a big role in whether you are going to survive or not. So today was an important lecture about the rate of climb. So we started moving from the steady level flight to climbing flight, and next we are going to discuss some important concepts specifically regarding service ceiling and absolute ceiling, because there is a point beyond which the aircraft cannot fly, and as you have already probably understood from some of these graphs, it is related to this concept of excess power, is that there is going to be a certain point where excess power is simply not going to be there, and so that limits your height at which you are going to be able to climb. So this is something we are going to look at in the next lecture, and I'll see you at that time. See you then.